Hello grade 12s. In this video we're going to be studying the theory and working through problems involving atomic spectra. Atomic spectra is not a very big section in these questions or big section of your question paper, but of course if you are interested in getting a distinction then it is very important to you. After this video I've created a video that involves an exam question. So an exam paper question, and there I bring together all of the topics, your photoelectric effect and atomic spectra, and we see how these topics can be tested together. So when we study atomic spectra, there are two types of spectra we're going to study. We'll start off with emission spectra. And we say an emission spectra is formed when certain frequencies of electromagnetic radiation, in other words light, are emitted. So emission spectrum is light emitted due to an atom's electrons making a transition from a higher energy state to a lower energy state. I'll explain this in a lot more detail in the video as it follows. We then have what we refer to as atomic absorption spectra. An atomic absorption spectrum is formed when certain frequencies of electromagnetic radiation that passes through a medium, normally a cold gas, is absorbed. So when we have an absorption spectrum, then we find that light is being absorbed, and we end up with a picture based on what has been absorbed. Now you might wonder why we study this. Using these principles, we're able to tell, for example, what stars are made up of. That it helps us with this. Based on the light that they emit, based on the light that they absorb, we can tell that different stars are made up of different atoms. For example, our sun. We know that our sun is mainly composed of hydrogen and helium. How do we know this? Based on us studying atomic absorption and emission spectra from the sun. This section of study is called spectroscopy. So if you go into university, you'll actually study light from certain atoms using what we refer to as a spectrophotometer. But I don't want to go into too much detail about that because you won't be tested on that. Let's hop into the emission spectrum. There's a lot of theory in your book about emission spectra and about atomic spectra. Most of it is irrelevant to you. If you page along, you're going to see a table which compares emission spectra and absorption spectra. You basically just need to know that. Promise. Or I hope so anyway. Okay, that's what I've seen from all of the papers that I've looked through, from all of the questions that I've seen. A lot of the stuff in your book is really just extra details. So they say, an emission spectrum consists of a number of bright lines corresponding to specific frequencies of light. They're observed when gas at a low pressure is obtained in a glowing state. So what basically happens is we can heat up the gas, okay? Or what we can do is we can take a metal salt and it's evaporated and viewed through a diffraction grating. Most of the time you guys are going to deal with a glowing gas. So remember, we're going to heat up the gas, often using electricity. What will then happen is that electrons within the gas's atoms. So let's say we're taking hydrogen gas. We will put it in a tube and we will heat it up. When we heat it up, the electrons, so remember our hydrogen atom is made up of a proton. Around that proton we have orbitals. Orbitals are basically just spaces in which you can find an electron. So we're going to have multiple orbitals. Okay, I'm not drawing them very well, but I think you guys get the picture. When our hydrogen atom is in its most stable place or state, the electron is in the first energy level. What will then happen is we will heat it up. We'll heat up these atoms. And then when they say the electron becomes excited to a higher energy level, that basically means that this guy over here is going to move from energy level 1 to a different energy level, maybe energy level 3. You see? And then my electron will be there instead. That happens when we heat up the atoms. But after a while, since electrons want to be stable, what will then happen is that the electron will go back to energy level 1, where it actually belongs, where it's most stable. We call that the lower energy level. When it does so when the electron goes from the higher energy state back to its original state, remember, it is losing energy. It's giving off the energy that it had gained. The energy that it loses, it gives off in the form of light. So it's going to emit light. Okay, so the atoms of the element, the hot gas, will emit energy in the form of light photons. They say the frequency of the emitted photons depends on the size of the electron transitions between energy levels. So depending on which type of gas we are heating up, we will have certain frequencies of light being emitted. Hydrogen does not emit the same light as helium, which does not emit the same light as neon or any other gas on our periodic table. The frequencies of light that it emits is specific to the type of element we are dealing with. So remember, we studied this continuous spectrum of visible light. We call it white light. It ranges from red all the way to violet. An emission spectra is filled with black, right? But you're going to see certain specific frequencies, these little straight lines of color. These are specific frequencies of light that would have been emitted when the electron travels back to its lower energy state. And that gives us this emission spectra. Frequencies of light specific to the amount of energy released by specific electrons in specific elements of atoms. Okay, this helps us to detect, okay, in the stars, we're looking at stars, we're looking at planets, we're looking at the sun. This allows us to tell what type of elements are contained in these planets, stars, and sun. Alright, if you go onto Google and you search what is the emission spectra for hydrogen, helium, neon, nitrogen, you're going to find that they're all different based on the fact that different elements will emit different colors. So here's an example just to show you of how it would look when we heat it up. I've already explained this to you, where we go from a higher energy state to a lower energy state, and then we would emit light. But often they like to make use of this diagram. So notice my electron goes from energy level 1 all the way to energy level 3. The energy that it has absorbed, right, that is the energy that was added by heat or by electricity that heated up. After it's in its high energy state, it then drops down to a lower energy state, which can be in between or it can be its original energy state. And when it does so, it emits light. Okay, whenever you see downward arrows in one of these diagrams, you know it is an emission spectrum, not an absorption spectrum. Take note of that, please. If the lines go down from a higher energy state to a lower energy state, or a higher energy level to a lower energy level, we're dealing with an emission spectrum. Now, the other type of spectrum that you can deal with is the absorption spectrum. The absorption spectrum consists of a continuous spectrum in which a number of dark lines, missing frequencies, are going to occur. So here's an example of an absorption spectrum. Notice we have this continuous spectrum, but then there are few lines, few frequencies that are missing. In order to obtain an absorption spectrum, what we do is we view white light through a prism while passing it through a cold diluted gas. So you basically have a gas and light on the other side, and since that light is passing through the gas, the atoms in the gas are going to absorb energy from the light. And the leftover light will continue to travel through to whatever is detecting the light. So what the detector detects misses the frequencies that the cold gas is going to absorb. Okay, so the electrons within the gas's atoms absorb energy and make a transition from a lower to a higher energy level. So going back to this diagram over there, what we're going to find is if you simply have a diagram in which we just have lines up where it goes from a lower energy level to a higher energy level, then you know that it is an absorption spectrum. That's what you're going to see, right? The atoms of the element, the cold gas, will absorb light photons. That is why there are frequencies that are missing over here, shown by the black lines. The frequency of the absorbed photons depends on the size of the electron transitioning between the energy levels. Okay, and that is specific to different elements. So again, your emission spectrum, a whole lot of black and a few frequencies that are going to occur. Absorption spectrum, a continuous spectrum, but then specific frequencies that are not in the spectrum. That is basically the difference between an absorption spectrum, and an emission spectrum. So now I'd like to go through a few examples. These should be simple examples, I hope. They say, which one of the following photons has the most energy? A photon with a wavelength of 400 nanometers, or a photon with a frequency of 4,3 times 10 to the power 14 hertz. You can't compare wavelength to frequency just by looking at it. We're going to have to convert one of these to, frequency, or the other to wavelength. So what we're going to do is we're going to go and actually what we could do is calculate the energy. Sorry guys. You could do what I said a moment ago, but to make the calculation complete, you can calculate the energy of A and you can calculate the energy of B. So let's do that. We know that energy is equal to, for this one, since we're given wavelength, it's equal to hc over lambda. Planck's constant is given as 6,63 times 10 to the negative 34. C is a constant given as 3 times 10 to the power of 8. Both of these are on your formula sheet. And this is divided by the wavelength of 400 times 10 to the negative 9 meters, because it's nanometers. Plugging all of this into your calculator, we get an answer of 4,97 times 10 to the negative 19 joules. We can do exactly the same calculation for B. We say E, however, is equal to H multiplied by F, since we were given the frequency. Planck's constant is 6,63 times 10 to the negative 34. The frequency is 4,3 times 10 to the 14 hertz. We plug all of this into our calculators and we end up with a value of 2,85 times 10 to the negative 19 joules. So in the end, remember they asked which photon has the most energy. We find that this photon A, which had a wavelength of 400 nanometers, has the most energy, since it is higher than 2,85 times 10 to the negative 19. Energy, guys, measured in joules. The next question says, which photon, A or B, can be associated with red light, and which one can be associated with violet light? You now need to remember the work that I covered in the section on the photoelectric effect. There I said that red light has a frequency that is low because its wavelength is long. Violet light compared to red light has a frequency that is high because its wavelength is small. It has a very short wavelength. But energy is related to frequency. So when something has a high frequency, it has a high energy. And when it has a low frequency, it has a low energy. So the substance that has the high energy will be violet, whereas the substance with the low energy will be red. And that is the answer to the first example. On to example 2. Here they say an electron falls back from an excited state to the ground state. If it goes from excited to ground, ground is the stable lowest state. If it goes from excited to ground, you need to know that we are dealing with an emission spectrum. They say it emits light, a light photon, with this wavelength, 500 nanometers. Determine the energy of the photon. It's actually a rather simple question. We're just going to say E equals hc over lambda. Plug in Planck's constant, 6,63 times 10 to the negative 34. C is 3 times 10 to the power of 8. And lambda is 500 times 10 to the negative 9 meters. We plug this into our calculators, guys, and we find an answer of 3,98 times 10 to the negative 19 joules. And that is the answer to example 2. We have one more example, that is example 3. It seems I haven't copied it in, so I guess you'll have to go through that one on your own, but I'm sure that it will make sense to you guys. It says for enrichment, so it means level 4, we're introducing, a little bit of extra there, okay? But in the next video, as I explained at the beginning, I'm going to be going through an exam paper, so please make sure to watch that video. Thank you, grade 12s.